In this chapter, we're going to talk about correlation and regression. Data for single variables is called univariate data, but most of the real-world models have more than one variable, and this is called multivariate data. In this chapter, we'll study bivariate data, that is, the relationship between just two variables. Now, in this class, we won't get into anything more than two variables, but if you were to take an extended portion of this class, that's probably where you would continue to deal with more than one variable. So when dealing with two variables, you want to be able to plot this on an XY grid. And we're going to create what are called scatter diagrams. And from there, we're going to talk about correlation. Okay, so the objectives here are to draw and interpret scatter diagrams, describe the properties of a linear correlation coefficient, compute and interpret the linear correlation coefficient, and explain the difference between correlation and causation. Okay. In these cases, we're interested in whether two variables have some kind of relationship. Okay. So, very often, when you're dealing with two variables, and if they have some sort of relationship, one of those variables will be called the response variable, and that's considered the dependent variable or the output variable. Okay. And it's a variable whose value can be explained by the value of the explanatory variable, which is the independent or the input variable, also known as a predictor variable. So that actually has two names. Okay, so the explanatory variable or the predictor variable is essentially the input, and the response variable is the output. Now, if there is causation here, then we can say that as the explanatory variable changes, the response variable reacts to it, okay, in some sort of way. So think of this as a cause and effect action, if there is actually some causality going on here, which again, we will talk about the difference between two things being correlated and one variable causing another variable to change. And they're not the same thing. Okay, so draw and interpret scatter diagrams. A scatter diagram is a graph that shows the relationship between two quantitative variables measured on the same individual. Okay, so in this scatter diagram, each individual is represented by a point on the diagram. The explanatory variable is the x value. That's usually on the horizontal scale. Okay, so the independent variable is always on the horizontal scale. And the response variable y would be on the vertical scale. That's the dependent variable. Okay. Now, if there's one thing that you should take from this class, and still remember 5-10 years from now, it should be this, really. And that is that correlation does not imply causation. Just because two variables are correlated does not mean that one causes the other to change. You might be wondering, well, if one changes and the other one also changes at the same or at some sort of rate, aren't they, doesn't one cause the other? Well, let's talk about that. Well, one way that two variables can be related, even though there is not a causal relationship, is through what's called a lurking variable. Okay, so this is a variable that has not been accounted for thus far in the analysis. Okay, so it's better to explain this with an example. And maybe you can probably detect what this lurking variable may be just by the outrageous claim that's being done right here. So for example, ice cream sales and crime rate have a strong positive linear correlation. This means that as ice cream sales increase, so does crime rate. And when there's more and more people purchasing ice cream, crime rate just happens to also go up. Does this mean that local governments should shut down all ice cream shops to stop crime rate from increasing? So the question is, does one cause the other? Okay. Now that does seem a little outrageous, right? That just because you see an increase in ice cream sales and also you see a crime rate at the same time go up, does it mean that one causes the other? They are correlated. What we're saying here is that there is a strong positive correlation, linear correlation here, but it doesn't mean that one is causing the other. Okay, so the answer to this question is no. We should not close down all the ice cream shops to stop the crime rate from increasing. And what's happening here? Well, there's some other variable that they're both related to that we just haven't accounted for, or we haven't even talked about. And in this case, some of you might have guessed it, but the lurking variable involved is temperature. Okay. As the temperature rises, both ice cream sales and crime rate rises. Okay. Why did crime rate rise? People leave their windows open. People are able to easily get into people's houses. Who knows? So again, just because two things are correlated does not mean that one causes the other. So mathematically, you can't really prove that something causes another thing. All you can do is provide evidence to support such a claim. Okay, and that evidence would come from a mathematical correlation. Okay, but it won't actually prove that one thing causes the other. You need some more insight on that to make that definitive claim. Example 1. Given a table of values with corresponding height and shoe size for a college class, with height as the explanatory variable and shoe size as the response variable. Draw a scatter diagram. Okay. Now, height and shoe size, it's not actually very straightforward which one is like the cause and effect type of variable, but they're just saying that there might be some sort of relationship between your shoe size and your height, and they're saying that, well, the response, think of that's always your output. That's going to be on the y-axis, and your explanatory explains the response. And that's going to be on the x-axis here. Okay, and we have our data here. So your height is your x, and your shoe size is your y. And we have various heights. Now, each one of these rows is one individual. This particular individual has a height of 54 inches, but a shoe size of 7. Okay, and then this individual has a height of 60 and a shoe size of 8. And what's interesting about this one, this is why I chose this one, is that there's another person who has a height of 60, but they has a different shoe size. Okay, so that's why when we plot these points, these are XY coordinates, right? On this grid, it's going to be all scattered. Okay, and maybe we'll see some sort of pattern. Okay, so that's the main purpose of creating a scatter plot to begin with. That's usually your step 1. That's your first order of business to see if there's any relationship between two variables. And just by visual inspection, you can kind of get an idea of what's going on. Okay, so let's go ahead and do that. All right, so I'm going to go ahead and write down the height down here. And this is in, I believe, inches. And the shoe sizes are going to be on this vertical axis here. And the units of that are just shoe size. Okay, so the way that we have this grid, I'm going to go ahead and start this not at 0, but at 50. Because our data, our x values of our data don't start at 0. So if we were to start at 0, we're going to have a huge gap. So I'm going to start at 50. That seems to be a good value. Now, each one of these lines, they're going to represent 1 inch. So every 5, I'm going to make a tick mark. So that's 50. And I'm just going to continue this pattern. Okay, so that's the horizontal axis. Those are the heights. I'm also going to show the scale for the shoe size here. And in this case, I am going to start somewhere around, I think 0 is fine, starting down here. And then each one of these will be 1. Okay. I chose this range of values for x and y such that all my data values can actually fit there. Because if I look at the smallest height, I find that I think 54 is the smallest. So I know this is going to encompass that. And the largest height is 74. So it's good on the x scale. It's going to cover all that. The shoe size, the lowest goes from 7 all the way to 11.5. So this definitely, it's all going to fit in this window. Okay. All right. So now I'm going to start just plotting each one of these points. So that first row, 54 and 7. Here's 54. 7 should be right there. So I'm going to do that for the rest of these. Okay, so here I have a completed grid here. Now, will you have to do this all the time by hand? Well, we actually have technology that can actually do this for you in practice, right? Also on your calculator, you actually have the ability to do that too. So if you were to put this X list in L1 and the Y list in L2, and we're going to go through these procedure right here that's listed below, making a scatter plot using a calculator. Okay, we're here on the calculator. Let's go ahead and input this data in there. Go to stat, edit. Okay, let me just go ahead and I'm going to type 54, 57, 60, 60, and so on. Okay, so I'm happy with those inputs. Let's go ahead and back out completely. Let's go to second quit. Now we're going to go over to stat plot. So we go to second stat plot. It's at the top left. On the top row, it's in blue, so you have to press second first. And I notice that all my plots are actually on. You want to, in this case, we just wanted to have one of the plots on. What you can actually do all at once, you can go down to the fourth option here and just turn them all off at once. That'll be easier for me. Enter. And it brings you back to the home screen. Just press enter again. Done. So again, I'm going to go back to stat plot. They're all turned off now. Okay, so that first one, let me go ahead and turn that one on. And the type I want is the one that, let me just show you. It's that first one. You see how it's just like a bunch of dots just scattered around. That's the one I want. So it's blinking over, so I'm going to press enter. That way it's highlighted. And you notice that now we have an X list and a Y list and something says mark. Okay. Our X list, we're going to make it L1 and our Y list L2. It kind of automatically did that, but if it had anything else, just make sure you have the correct list there. Mark, the purpose of this is just for visual. Do you want the points to look like little squares or pluses or dots? It's really up to you. The squares are fine for me. Okay, so I'm going to go ahead and quit out of this. Second quit. And I'll clear that out. I'm going to press zoom. And then it should be the ninth option, which is zoom stat. Yep. Press enter. And does that plot look familiar? All right. Now it kind of looks like ours. The one on the calculator is a little bit more zoomed in. It just kind of has all those values in a much tighter window. I do have in my plot just a lot of empty space at the bottom, but it's basically the same. And if you were to press trace, you'll see that, and then start pressing the arrow keys, you can see that you can actually go to each point. Okay. Okay, so what do we see here? Let's go back to the page here. Upon first inspection of the scatter plot, I would say that there tends to be some sort of upwards trend. You see that? As the height of a person increases, so does their shoe size. Okay. Now that's not very mathematical. Okay. We want to have a more robust method of explaining that these two variables we believe are correlated. Okay, that they're related in some sort of way. So we're going to go through a few different ways to describe the overall pattern. Okay, so after constructing a scatter diagram, we want to describe the overall pattern. And there's essentially three major aspects that we want to describe. Okay, and the first one is going to be the form. The second, once we know the form, we want to know what direction. And then the third would be the strength. Okay, and we'll explain what those three mean in detail right now. Okay, so what do I mean by form? Well, in broad strokes, you can actually just say, do we see something that looks like it's linear? Do we see some sort of pattern, but a non-linear pattern? Or do we just see no relationship at all? And then I'll show you some examples of what I mean there. Okay, so again, a relationship is linear when the points on the scatter diagram follow some sort of general pattern of a line. Okay, you can kind of imagine like a straight line fitting the data. Okay. A relationship is considered to be nonlinear when the points follow a general pattern, but it's not a straight line. Okay. And when is there no relation or no correlation? Well, when the points don't show any pattern at all. Okay, it just looks like a bunch of noise. Okay, so what are the examples here? Okay, so this one is an example of something that's linear, right? You can see how you can kind of like fit a line, if you will, some sort of best fit line, a straight line. This one's also linear, right? Now this next one, you can see that it's not linear, right? It doesn't have a straight line, but there is nonetheless some sort of pattern, okay? There is some sort of predictability, okay? I can, for example, this value right here, I can predict that it probably fits this value right there. You see that? For this value right here, I can see that I can predict it to be probably around there. I have a good chance of predicting that. So that's what we mean by the form, okay? Again, this is another pattern that we see, but not necessarily a straight line. So it's nonlinear. And then this next thing here, well, you might be able to say, well, I can fit a straight line right here, okay? And that kind of seems like it fits. And I would say that, yeah, it's true, but we're going to talk about in just a bit that something that has a slope, if you remember from your algebra classes, a horizontal line has a slope of equals 0, meaning no matter what x value we have, it predicts the same y value, right? There's no variation here. You see that? It just predicts all the same y value. Okay, so essentially the response variable doesn't respond to a change in your explanatory variable. Okay, so this is just a bunch of noise. Okay, the response, there is no signal essentially. You can think of this response variable not being affected by the explanatory variable, because the explanatory variable can change, but the response variable tends to just be at the same level, unchanged. The other aspect that we want to talk about is the direction. So once we've established that something is a linear relationship or a linear association, then the direction can either be positive or negative. So if I look at that previous example, the two that were linear here, these two, if it from left to right it is increasing, if it's going upwards, that's going to be a positive. And if from left to right, if it's decreasing, that's going to be a negative correlation. What type of association in the previous example of the height versus shoe size did we have? Okay, so we're only talking about, what have we learned so far? Just form and direction, right? So what's the form of our data? Well, is it linear, nonlinear, or no relation? Again, I would say I can probably fit a straight line right through there, right? It has some predictive power. Okay, like for example, I can probably predict someone who has a shoe size of 55 to be somewhere around here, probably like a 7. You see that? Okay, so it's definitely linear. Now in what direction? Well, from left to right, it looks like it's going upwards, so that's a positive. So far, we can describe this association as there is a positive linear association between the height and shoe size. Now, you notice that we didn't really do much math there. All we kind of did was just looked at something and we gave it names, right? But it didn't seem very robust or very rigorous, right? So that's where that third attribute comes into place, and that is the strength, okay? And we're going to introduce a thing called the linear correlation coefficient. This is going to be a measure of strength and direction of the linear relationship between two quantitative variables. Now, this is a theoretical value, okay? Like if I were to say, what is the average height of everybody on Earth? Well, unless I have access to everybody on Earth, I don't know that number. So the best I can do is take a sample, a pretty large sample, right, to be able to estimate that value, okay? Just like in this case, I don't have access to every person in the world to figure out if their height and shoe size are correlated, but instead we take samples. Okay, so what we have is a population parameter for this correlation coefficient, and we call that rho. We usually use Greek letters to represent population parameters. That's the population correlation coefficient. But again, since we don't usually have access to population data, we take a sample, and the sample correlation coefficient is just the lowercase r. Okay, so that Greek letter rho, it looks like a P, but that's our version of r. Okay, now how is this calculated? Well, it's a little complicated. You would take the x list, each value in the x list, subtract off the sample mean, and divide by the sample standard deviation. You get that quantity. If you recall, this is actually really a z-score. The z-score of the x. And the same thing for the y. This would be the z-score of that y variable. Multiply them for each individual, and then sum them all up. Okay, and then divide that by n minus 1. Okay, you can see how that could be pretty tedious to do. And luckily, our calculator can actually do all this for us, because all you really need to do is insert a list for your x values, insert a list for your y values, and your calculator should be able to calculate this r value, this sample correlation coefficient. Another way to calculate this value, there's another formula for that. If you actually have the sample standard deviation of the x value, sample standard deviation of the y values, this is what's called the covariance between x and y. It's beyond the scope of this course. It's more of an FYI. In fact, it's defined down here, that SX. Now, the more important thing about this value, this R value, the sample correlation coefficient, is this, okay? This is designed in such a way that the R value here only produces values that are bounded between -1 and 1. That's very important. It won't be anything outside of that range. And that's really nice. Okay, so that's really the most important thing to get out of this. So this sample correlation coefficient measures the strength and direction of our relationship between our two x and y variables. And that value is some value between -1 and 1. Okay, and whatever that value is gives us an idea about the strength and the direction of their linear correlation. Okay, so let's go through a few examples here describing that. Okay, like I mentioned before, the properties here are that this R value always lies between -1 and 1 inclusively. And let's just talk about the extremes here. What if we get an R that's exactly a +1? Okay, there's only really one way for this to happen. Okay, that's if all the points actually fall on a straight line. There's not one value that deviates from that line. Okay, so we call this a perfect positive linear relationship. Why is it positive? Because it's a +1. Why is it perfect? Because it's 1. And you can imagine that if r is equal to -1, well, again, the only way that that can happen is if all the data values lie on a straight line, but actually has a what we call a negative slope. So this is going to be a perfect negative linear relationship. Now, one thing I do want to mention is that this linear correlation coefficient only detects linear relationships. Okay, it won't detect any other type of relationship. It detects linear relationships. So positive R values correspond to positive association. Negative R values corresponds to evidence of a negative association. And then the R values that are closer to the more extreme values of +1 and -1 are stronger linear relationships than those that are more towards the center, which would be 0. Right? So if R is close to 0, then there's either little or no evidence exists of a linear relationship between the two variables. Okay. And then R closest to 0 doesn't necessarily imply that there's no relation. It's just that it's no linear relation. I'll give you an example when your R is close to 0 and there is some sort of relationship still, but it's not necessarily a linear association. The nice thing about R is it has no units associated with it. And then the very last thing is something we talked about in one of the first chapters, is that this R value is not resistant. And what does it mean for something to be not resistant? It just means that if you introduce outliers, then it'll actually sway this R value quite a bit. It's sensitive to changes that are extreme. Okay, now the following here is just going to be a rule of thumb. I want to emphasize this. It's not really set in stone here, but this is just more of a rule of thumb to describe the linear relationship using R. Again, this is not a robust method of describing, but it does give us a general idea. Okay, so your R values, again, they range from -1 all the way to 1, and 0 is right at the center. Okay, so I'm going to break this up into essentially 7 regions. Okay, so I'm going to call something like this -0.1. This will be +0.1. This will be 1, that center region. And then the next partition, this will be 0.4, and 0.7 seems to be around here. Okay, so let's go ahead and partition that. And I'm going to do the same thing for the negative, -0.4, and I think like -0.7. Okay, let's start with the very center. Okay, I did mention above that if you have R values that are very close to 0, then what we have is no linear association. I'll just say no linear relation. So no linear relation. If I move over to the right here, if you get an R value that comes out to be between 0.1 and 0.4, well, these are our positive numbers, okay? But this would be, since it's pretty close to 0 and it's not too close to 1, we're going to call this a weak positive, because it is positive, linear relation. Okay, again, this correlation coefficient only detects linear relationships. So all these are going to be linear. 0.4 and 0.7, well, it's not weak, it's not strong. We'll just call it moderate. However, it is still positive, linear relation. And over here, anything above 0.7 and between 1 is, we'll call that a strong, positive, linear relation. And then over here we have perfect. This is perfect, positive, linear relation. Okay, that's the only way that can happen is if this R value comes out to be exactly 1. And I'll show you some examples of how that can happen. And now take a lucky guess what the left side is going to be. Well, between -0.1 and -0.4, well, it's pretty much a mirror image of the right side, right? It's a weak, not positive, but negative, linear relation. Between 0.4 and -0.4 and -0.7, we're going to have a moderate negative. It's in the negative region here, linear relation. And of course, over here, it's going to be a strong negative linear relation. And of course, -1 is a perfect negative linear relation. All right, so below here, we have some examples of what that is. All right, the first one. You notice that there's a straight line that passes right through all the points, and none of the points deviate from that line at all. This line goes straight through all the points. So that's the only way you can get an R equals 1, and it's in the positive direction, right? Here's an example of, this is an R equals 0.9. You can see how it's a pretty strong correlation. You see how the points don't really deviate that much, right? There seems to be a pretty tight band that all those values are within, and it's in the positive direction. Over here we have what's called, well, this is 0.4, so it's a little bit in between weak and moderate. So you see how the band is a little bit wider, right? So it's not very, the predictive power of this, if you were to draw a straight line through here, right? The predictive power of that is a little bit weaker, because if I were to use this value here, if I wanted to predict a y value for this, I would actually use this line. And as you can see, there's probably less confidence in that value, right? Because this band might actually be a little bit wider, as opposed to something like over here, where you actually, the predictive ability of this model, this best fit line, is a little bit tighter. You see that? So those values are a little bit closer than it is in this case. This one is a straight line, but it's in the negative direction, right? You can fit a straight line through there. That's where you get, that's the only way you can get an R equals -1. And of course, there's another negative association right here, but with the slightly wider band here. It's in the negative. Over here is, and that's negative 0.9, so that's in the strong negative linear correlation. And over here we have a much wider band, right? There's probably an outlier right here, but who knows? But yeah, you can see how if you were to fit a straight line, the predictive power of this model is not as powerful as maybe this one here. Okay, and then here's another one here. You see this? Now this is an example of an R that's close to 0. Okay, you see how there's not really any way to predict a value here, right? It just seems like a lot of noise. I don't see like a general pattern. I can't tell if it's like here or here, not really, because these values bring it this way. So that doesn't seem like there's anything going on. In fact, if you were to fit a best fit line through there, it would actually, the best fit line would probably be something like this, meaning that no matter what value of x you have, your best estimate for that is just the average of the y values. So meaning that your response variable does not respond to your predictor variable, your explanatory variable. So that means that there's no signal that it's receiving. So there's no relationship between these two variables. Okay. Now here's another example of, and this was what I was talking about before, that if you have an R also close to 0, so these are similar to each other. However, I can tell that there is some sort of predictive ability here, right? Again, this correlation coefficient only detects linear relationships. There's definitely a relationship here, but it's just not linear. Okay? And how do I know that there's a relationship? Because, again, I can tell that I can predict just by the pattern here. Like, for example, I can predict that value to be right here, right? Like over here, I can predict that value to be that value right there. Right? So it's, you can still fit some sort of model to this data. It's just non-linear. Okay, and this R values, these correlation coefficients, only detect linear relationships. All right, so how do we actually calculate this correlation coefficient R that we've been talking about using the calculator? Well, I did show you the formula before, but there should be a much easier way to do so. And there is. We're going to be using a function called linreg ax plus b. There's actually two versions of this in your calculator. They have one that says linreg ax plus b, and I believe the other one is a plus bx. Okay, it doesn't matter which one you're using. The one thing that matters is that the value next to the x is the slope, okay, no matter what version you're using. Now, what I do want you to do first in your calculator, and this is just done once in your calculator, and you'll never have to do it again unless you reset your calculator's memory. And we have to go to diagnostics on in your calculator. Let me just show you how to do that on the calculator. All right, let's follow these directions. It says, enter the catalog menu. Okay, so where's catalog? Well, this is somewhere that we haven't actually explored in this class so far. But if you see that button 0 down at the bottom left, you see in blue right above, it says the word catalog. So anything in blue, you have to press second, and then that button. And this literally has a list of every single function that is in your calculator in alphabetical order. And we're going to look for the one that says diagnostics on. Okay, you just have to scroll down until you find it. Okay, it's not going to take too long. We'll get there pretty soon. Looks like, there we go. I see diagnostics on. This just adds extra detail to this linreg ax plus b function. Okay, this is the purpose of this. So I'm just going to press enter there. It's going to bring it back to the home screen, and then press enter again, and it should say done. Yep. And from there, we're going to go ahead and, again, I do have data in our calculator, which was the data from the height and the shoes example. Let me just, it's right there. So let's go ahead and go to Stat. We're going to go to Calc. And the only thing that we've actually used in this menu has been one-var stats. The other function that we're going to use today is that fourth one, linreg ax plus b. Again, there is another version of this. If you go scroll down a little bit further, there's a plus bx. It's the same thing. It's just that the a in the fourth one represents the slope, and then this eighth one right here, the b represents the slope. So it's just a matter of recognizing. I'm not sure why they actually have this function in your calculator, or two different ones. There's really no need for it. I'll just use that first one. My data list is in L1 and L2. Everything else, you just keep it blank. And let's go ahead and calculate. And what you'll see here, the first thing that you see is something that looks like y equals ax plus b. Okay, that's the equation of a line. We'll talk about that in the next session when we deal with least squares regression. You don't want to pay attention to those first three. What you want to pay attention to is just the R value. Okay, that R value is your correlation, 0.874. So the correlation coefficient here is R equals 0.874. And just based on what we just talked about previously, 0.874, that looks like it's in the strong positive linear relation category. So we can say that there is a strong positive linear association between height and shoe size. Okay, that's it for now. See you in the next section.